Faculty Development Program. On behalf of Kalasalingam University, it is my pleasure and privilege to welcome you all to the second day Faculty Development Program of Session 2. It is my pleasure to introduce our resource person, Dr. Shripad Karmalkar. He is a professor of electrical engineering and head of the Teaching Learning Center at IIT Madras. His twin interests are semiconductor devices and education. His recent research has focused on nano devices, power devices, solar cells, and gallium nitride (HAMTs). He has received the Vikram Sarabhai Award for Research in 2006, IBM Faculty Award for Research and Teaching in 2007, President's nomination to the IIT Council for contributions in education, science, or technology for 2019 to 22, and VLSI Society of India Best Faculty Award for teaching, popularizing and creating some of the best minds in microelectronics in the last 30 years in India in 2021. His video lecture series on semiconductor device and research skills hosted on the internet are quite popular. He is an associate editor of IEEE Transactions on Education and chairman of AICTE Board of PG Education and Research. He was chairman of South Zone JW 2007, a member of the National Working Group of DIT GOI in Nanotechnology, and member of AICTE's Board of UG Studies. He has held visiting assignments at US universities, namely US Santa Barbara, RPI, and USC. Welcome, sir. And in this session 2, we are going to discuss about the nanowire devices. So our resource person, Dr. Karmalkar sir, is going to discuss about the structure, fabrication and mechanism underlying the current voltage characteristics of PN junction, Schottky contacts, ohmic contacts, and field effect transistors realized in nanowires. It will highlight the new effects that set in the bulk devices or shrunk to nanoscale, including the effect of the surrounding field. Now the stage is yours, sir. You can.
Sir, you're in mute, sir.
Yeah. The person introduced me is Dr. Bhuvaneshwari.
Yes, sir.
Okay. So thank you, Dr. Bhuvaneshwari. And the other person, Charles, am I right?
Yes, sir. I am.
Charles. Okay. So thank you, Charles, for inviting me.
Thank you, sir. Thank you so much for accepting our invitations.
It is unfortunate that we have lost almost half an hour in trying to.
Yes, sir.
Yeah. So what do you suggest? Shall we end on time or can I take 15 minutes more?
You can take, sir. You can take your own time.
So when is the next session?
The next session is by 2:15, sir.
2:15. So
we can.
We should give time for people to take their lunch and all that.
Okay. Yes, sir. We can start the next session by 2:30 also. No problems.
Yeah, we will see.
Adjust accordingly.
Yeah, we will see. Okay. Now, one thing is I would like this session to be interactive, because what I have found is only interactive sessions we are able to transmit at least a few concepts. Otherwise, what happens is people just hear, okay, and then they leave, and after some time, whatever they are exposed to vanishes. I normally use the analogy of photography, right? So those who are familiar with how a photograph used to be made, a film used to be made earlier. Nowadays, of course, people are using these cameras, CCD cameras. So after exposure, the film had to be developed, and even after development, the photograph would not remain unless you have a step called fixing step. Okay. So I give that analogy and say that unless we have interactions, we have question answers and so on, the concepts that are being discussed don't get imprinted on the minds of the audience. Okay, so let me begin with some interaction. I would like all those who have heard any talk of mine earlier in any program to please turn on your videos. All those who might have heard any talk of mine in any other program, please turn on your videos, or at least write in the chat. I will also use the chat. Let me see in the chat if there is any response. So I would like some responses so that, okay, so if you have not heard me, you please write no in the chat so that.
One of the participants has turned on the video, sir.
Pardon?
Rupan with Vita.
Yeah. Okay, some people have turned on. That is nice.
People have turned on, sir.
Yes, sir.
Yeah.
Yes, sir.
Okay, Rupanvita, what is your full name?
Rupanvita Das Mohapatra.
Okay.
Basically from Odisha, sir. But now I am in West Bengal.
Okay. So have you heard any talk of mine earlier?
No, sir.
Oh, no, that I thought those who have turned on the video, they are serious. But I hear. Okay, thank you. What about Ramya Jayachandran? She says yes. Can you please turn on your video, Ramya? Ramya, because she says yes. Okay, what about Bharat Shri? What is it that you wanted to tell me?
Sir, good morning, sir. Myself, Bharat Srinivasulu, research scholar in NIT Warangal, sir.
Okay.
So after my joining to NIT Warangal, I used to study to go through your videos in YouTube. So I use it to fundamentals of FET, modeling of devices.
Right.
So with your concept,
okay. Thank you.
so I benefited a lot.
Okay, so the videos you have seen, but not a live talk. Okay.
Yeah, yes, sir. First time this is time I'm listening to your live talk.
Okay, thank you. Anyone else would like to interact? Anyone else? You can turn off your video. That is fine. Now, let's see if anyone else. Ramya wanted to said that she has attended, but I don't see any further response from her. Ramya, can you please put in the chat? Is it that your mic, at least you can turn on your mic? We are doing this warming up so that when I get on with the talk, then there will be interactions, technical interactions. Okay, so this is a warm up for that. I don't know. Ramya doesn't seem to be responding. Right. Let me share my screen and start. Is my screen, is it visible?
Yes, sir.
Yes, sir. It's visible, sir.
Okay. Right. Now, in this slide, you can see some animals and, trees and so on. Can anybody tell me why these are here? On the slide, why are these here? Okay. So let me tell you. So IIT Madras campus is known for its flora and fauna. So we have deers moving about in the campus freely, right? And we have a large number of flora with different types of plants and so on. And we of course have some monkeys too. So I invite those who have not visited our campus to pay a visit sometime, at least to see the campus environment. Okay, now with that invitation, let me proceed further. Here is the outline of the topics that I can cover, though I will not be able to cover all of them because it all depends on the duration of the talk, right? So first we'll talk about nanowires, how they are grown and what are their parameters and shapes. Then we see how the characterization is done, what devices, how devices can be made using nanowires. And then we will point out some anomalies observed in measurements. That is, same device, if you see on a large scale, you get some characteristics, but when you reduce the size, the characteristics change. So what are those changes? We will see that. Then we will try to explain these observations by theory. Okay, so that is essentially the outline of the talk. Here is a diagram of a nanowire. So you have a substrate, and this is an example of a vertical nanowire made of silicon. Now, on the top, you have gold. This is actually a gold silicon alloy because, at the temperature at which the wire is grown, the gold silicon interface has a lower melting point than the melting point of gold and melting point of silicon. Okay, this is called a eutectic point. How many of you know this word eutectic? How many of you know this word eutectic? Can you please say, if you know the word eutectic, please type yes in the chat. Either Charles or Bhuvaneshwari can tell me how many yeses are coming in the chat. Yes, Bhuvaneshwari or Charles, any of you?
Yes, sir. I'm just looking on, sir. No one have typed. Only no is there.
Okay, no is there. So the
100% yes, Bharat Srinivasulu.
Bharat Srinivasulu. Okay, Bharat, please tell me what is this eutectic point. You can turn on your video and tell.
Someone has said mixture of components, sir.
Okay. Oh, you have to unmute. Bharat, you have to unmute.
Okay, sir. The melting point of the device where it gets melts. It is a melting point.
Melting point of what?
So crystal, silicon.
No. So silicon has a particular melting point and gold has a particular melting point. Okay. But wherever gold meets silicon, at that interface, the melting point of that interface is much lower than melting point of gold or melting point of silicon. This is a very important property. Okay. If any of you know phase diagram, any of you know? If you do not know, then you must review. Okay. Fine. Let's proceed further. So that is why you can see what is written here, gold silicon alloy. Okay. So an alloying will take place. A gaseous silicon precursor. Now I will come to what is the meaning of this precursor and so on. This is how a wire that is grown looks like. Okay. This is an actual photograph of a number of wires grown on substrate. One wire won't be grown, right? A large number of wires will be grown. It looks like a sugarcane field, right? Carefully look at the picture, and can any of you tell me what is the distance between the wires? What is the distance between the wires? You can please see in the chat, and Charles, you can tell me. Huh?
Okay, sir.
As soon as you get one response, you tell me. What is the distance between the wires?
In nanometer.
No, I want some exact number.
1 nanometer I've sent, sir.
Sorry?
1 nanometer. Rishabh Pachaya has sent 1 nanometer.
400
yeah.
nanometers. Another answer is 400 nanometers.
Okay, who is giving 400 nanometer as the answer?
Biplab Chatterjee.
Yeah, can that person please turn on the video? Can that person turn on the video, please?
Dr. Biplab Chatterjee, can you please turn on your video?
This is what is interaction.
Another one also given.
It will be better if you turn on the video because it will be interactive.
And please do it quickly so that we don't waste our time, right? Oh, okay. Who else has written 400?
Ritima Singh.
Ritima Singh.
Yeah, please. Can you turn on the video?
Good morning, sir. Can you hear me?
Yes, yes. Yeah, Biplab. Yes.
Sir.
400.
Yeah, I can see the scale.
Right. You can see the scale. Good. That is what I wanted to see if people are paying attention, right? As Biplab, which where do you belong? I mean, where are you teaching and what do you teach?
I'm teaching in Vardhaman College of Engineering, sir, Hyderabad.
Where?
Vardhaman College of Engineering, Hyderabad, sir.
Hyderabad.
Yeah.
Oh, I see. Okay, good. I also come from that place. Thank you.
Okay. Thank you, sir.
Okay. So as Biplab has said, see, you must see this 400 nanometer. This is how to read a photograph, right? So the distance is given as 400 from one end to other end, from this end to this end. This is the meaning of the scale, right? This much distance is 400 nanometer. And so Biplab would have sensed that if I take this distance between two wires, any two wires, right? Then it looks like the same as this distance, therefore it is 400 nanometer. He is right. Okay. Now, what about the diameter and height of the wire? Let's look at those points, right? So here are some more information. You can see that the diameter of the wire can vary from 6 to 600 nanometers. Okay. And the height, it can vary from 0.2 to 20 microns. Okay. Now, I would like someone to tell me 1 micron is how many nanometers? Please type in the chat answer. 1 micron is how many nanometers? And you should tell me if the moment you get an answer in the chat, please tell me.
Thousand, sir.
Again, 1,000, sir.
1,000.
Who is the person?
Bharat
Bharat
Srinivas.
Srinivas.
Okay, no, Bharat, I think he has answered. Anybody else?
Lima Rose sent 1,000, sir.
Who? Sorry, who?
Lima Rose.
Okay, can you please turn on your video, please? Lima Rose.
Yeah, 10,000 nanometers. Yes.
Yeah, I'm not able to see. Did you turn on the video?
Lima Rose, ma'am, are you there? Kindly turn on your video.
Okay, see, this is one of the problems of this online workshops. People should be all ready with their videos and interaction and so on. Without that, the online sessions are not effective, right? Anyway, so now I don't want to waste the time. Let me proceed further. So, right, 1 micron is 1,000 nanometers. 1 micrometer is 1,000 nanometers. So that will give you some idea. So in other words, 600 nanometers means how many microns? Okay, at least type in the chat. Lima Rose, ma'am, can you please type in the chat? 600 nanometers is how many microns? And as soon as you get an answer, you tell me, Bhuneshwari or Charles.
Someone has said Sridevi 0.6, sir.
Good. Sridevi 0.6.
Sir, 0.6 micrometer. Yes, sir.
Sorry, pardon?
0.6 micrometer.
0.6.
0.6.
Yes, 0.6. Rupan,
Yes.
that's right. Okay, 0.6.
Yes,
So this is important because I should see both height and this diameter on the same scale. Then only I will understand, get a feel of how the wire will look like. So you can see the diameter is 0.6 nanometer and height is 20. That means, suppose you take that extreme, then it means 0.6 and 20. So 20 by 0.6, almost 35 times. The height is 35 times the diameter. So like that, you can have either short and stout wires or very thin and long wires. Okay. Next, let us look at the material that can be used to make these wires. It can be silicon, gallium nitride, zinc oxide, bismuth sulfide, silicon germanium, cadmium sulfide, etc. Now, the doping can vary from undoped to 2 into 10 power 18 per centimeter cube. And the contact, it can be ohmic or Schottky. Okay. Do people know the difference between ohmic and Schottky contacts? Any one person, please tell me what is the difference between ohmic and Schottky contact? What is the difference between ohmic and Schottky contact? Yes, anyone? We have 95 participants now. I'm sure there will be some who know what is the difference between ohmic and Schottky.
Sir, I don't know exactly, but what I know is between metal and metal, that is called ohmic, and metal and semiconductor, it is called Schottky.
No.
Hello, sir. Hello, sir. This is Biplav again, sir.
Right.
Sir, in Schottky contact, the work function of metal is more compared to the semiconductor, but the reverse is for ohmic contact, sir.
Okay, so that is also not correct. Let's get some more answers, right? Because my point is that out of this session, people should take away some concepts, at least so that they feel, oh, okay, we have learned something new. If I go on talking
Sir,
ideas without clarifying, right, without checking whether people understand them. Yes, who else? Someone. Yeah.
Schottky diode is having lightly doped silicon and ohmic is having heavily doped silicon.
No.
Doping of the silicon.
Okay, you are not totally wrong. You are not totally wrong, but that is not how it is defined. The construction, maybe you are correct, but the definition of what is ohmic and what is Schottky. So you are right. You have told one how an ohmic contact looks. That is what, and how a Schottky contact looks, right? So you are not wrong. That is why
Yes.
the basic definition.
Sir, it may be based on the work function difference between metal and semiconductor.
Yes, it is based on work function difference. That is true. But fundamentally, now let me tell you, ohmic contact means a contact which has a linear current voltage characteristics. Linear current voltage characteristics, right? Linear means what? If I plot I versus V, I'll get a straight line passing through origin because it's like a resistance, Ohm's law. It follows Ohm's law. Ohmic contact is a contact that follows Ohm's law. And what is Ohm's law? Ohm's law, we know?
Constant temperature.
Resistance is given by voltage by current. That is what is Ohm's law, right? So in other words, the contact behaves like a resistive contact. Okay. Now, but what is a Schottky contact? A Schottky, then can you tell me what does the word Schottky mean? What does Schottky mean? Anyone? Okay.
Attach aluminum material with silicon, semiconductor material, I think.
Who is the person speaking?
Chandrasekhar from Rajahmundry, Andhra Pradesh.
Thank you for responding. Right? It doesn't matter whether your answer is right or not. The interaction is more important. Okay. No, that is actually not correct. So Schottky is the name of a scientist who gave the theory for this kind of contact. And what is this contact? So wherever the current voltage curve is non-linear, whenever the current voltage curve is non-linear rectifying, okay, then it is called Schottky contact. I think I should plot and show you. That may be better. Then you will appreciate it better. Okay. So let me plot it here using this. So suppose this is the graph. This axis is current and this axis is voltage. Are you able to see these two lines?
Yes, sir.
Okay. So suppose this axis is I. And this is V. Okay, IV. Now, ohmic contact. What is the V? V is the voltage across the contact, meaning it is like this. Let me show that also. If I take, supposing I apply positive voltage to this dark part, which is a metal, okay, and a negative voltage through the silicon substrate. Right, this is negative. So, or I can even put negative here because top I'm connecting positive and bottom negative. Now I'm talking about the characteristics of this part. Is my cursor visible? When I'm showing this cursor, is it visible?
Yes, sir.
Yes, sir. Yes, sir.
Yeah. So this part is the contact. Now, the current voltage curve, if it is like this linear, and you can see that whether the voltage is positive or voltage is negative. For a given voltage, the magnitude of the current is same. For a given voltage, magnitude of current is same. The current, for positive voltage, current may be one direction, negative voltage, other direction, right? But magnitude is same. This is meaning of an ohmic contact. As against this, suppose your current voltage curve turns out to be like
Sir, your mic is muted, sir. We are not audible.
oh, when just now or when did you
Yeah,
get?
Just now, sir. Just.
Okay, okay, right, right. So if you get a curve, current voltage curve like this, you can see that for positive voltage, current is high, negative voltage, current is low. So this is a nonlinear current voltage curve, right? And rectifying, or you can say rectifying. Now, Schottky is the name of the scientist who gave a theory explaining why a current voltage curve is like this, rectifying. That is why that contact is referred to as Schottky contact. This is the difference between ohmic and Schottky. Now, when you want to build such contacts, as somebody said, it is found that if your doping in the semiconductor is heavy, then you can build ohmic contacts. But it is not necessary that only when the doping is heavy, you can build ohmic contacts. That's why that is not good. That definition is not correct. By and large, yes, it is true. Usually you will find ohmic contacts with heavily doped semiconductor, right? And whereas for Schottky contacts, the doping is not heavy, but that is not the correct, because you can show that even with lightly doped semiconductor and some metal, you can get an ohmic contact. Okay, fine. So that is Schottky and ohmic contact. So you can get both types of contacts. And what are the kind of metals? So which can be used to make such contacts? Titanium, gold, platinum, iridium, tungsten. Then, or you can put P plus silicon, right? Or P plus of another semiconductor.
So sorry for the interruption. Any difference is there for Schottky diode and Schottky contact?
No, no.
So what is the Schottky diode, sir?
The word diode means anything that has two terminals. Diode, di means two. Ode means terminals. A device with two terminals is diode. Okay.
So what is Schottky diode, sir? Here is Schottky contact.
Same. No. So, okay, it is like this. So if I refer, okay, let me explain it like this. The both words, they almost mean the same. Almost I am saying. So let me tell you what. If I talk about this whole structure, I can call it as a diode because it has one terminal here and another terminal is the substrate. So the whole structure can be called as a diode. Whereas if I refer to this interface or contact alone, right? So a Schottky contact would mean this region. This region is Schottky. This interface is Schottky. Schottky diode means this whole structure. So you can see there is almost not much difference. So you can say that the Schottky diode consists of a Schottky contact and some semiconductor region which may offer some resistance. Does it clarify? Does it clarify your doubt? Who was the person who asked?
Yes, sir.
Yeah, who was the person? Can you please tell your name?
Yes, sir. Chandrasekhar, sir.
Oh, Chandrasekhar. Okay. And please tell, what are you doing?
Sir, I am professor of EC department, sir. ISTS Women's Engineering College, Rajahmundry.
Okay, good. Thank you. Okay, so that is what it is. STM and AFM tip, that is scanning tunneling microscope and atomic force microscope tip. So these things. Okay, so you can get ohmic or Schottky contacts due to any of these reasons. So let us proceed further. We'll understand what it means. Now, what about the shape of the wire? Okay. Now, shape of the wire. Are you able to see the title or is it getting covered?
Yes, sir, it's visible.
Because for me, something is covering that. I don't know how to push it up. But for you, it's clear, right?
Yes, sir, yes, sir, it's clear.
Okay,
Yes,
so
sir,
maybe
clear.
only for me. Okay, these are the shapes of the nanowire. So cross-section of the nanowire can be circular or rectangular or triangular, right? And the thickness can be 6 to 600 nanometers. And the diameter length, I've already told you, 0.2 to 20. So cross-section. So here, for example, this wire, if I take a cross-section, how will it look? It can be any of this. Okay, now we talked about the contacts and so on. So I am now telling in practice how contacts between wires and other regions are made and how do they look like. So here is,
Excuse me, sir.
yeah.
Usually, whenever you are discussing about wires, it's mostly in terms of circular, no, sir?
Not necessary. That is the point.
Yeah. Okay.
It is just that wires we have come across are circular. That is why we think wire means it should be circular. It is not necessary. Okay, it can be square cross section. It can be a triangular cross section. Even that can be a wire. Okay. Now, so you can see here, this is an example where you have two regions of semiconductor and a thin wire connecting between them. Okay. Similarly here, you can see again two regions and then in between there is a wire. This is another example. Tips, you can see some probe tips, okay, coming out, and then in between them there is a wire. Finally here you can see this kind of wire growth, and then an effort is being made to make a contact to these wires from the top using a tip. This is platinum iridium tip. Why are we doing this? Because we want to characterize the wire. We want to find out properties of the wire, what is the doping and all. So we want to pass current and measure voltage and all these things we want to do. I have to make a contact. So this tip is being made. This tipping is being used to make a contact. Okay. And here you have the substrate at the bottom. Now, wires can be either vertical or horizontal. So you can even, so far whatever I've shown, these are all, this is vertical wire, for example. But you know, these are not necessarily vertical, they are horizontal. Okay. They can be vertical also, but so both are possible. Now, field effect transistors, which are made out of the wire, generally they are horizontal. We will see some structures for this. Look at this. How contacts can be of different types. So now you can see vertical wires here. And this is the semiconductor material that is making a contact to the wire from the side. Can you see that? So this semiconductor is making a contact to the wires, these wires, from the side. Okay. Whereas this substrate is making a contact to the wire at the end. Okay. So that is why we have two types of contacts, side bonded and end bonded. This is an example. So this is a horizontal nanowire placed on a metal. Placed on an insulating substrate. And then on the two sides, you have put two strips of metal on it to make a contact. Okay. Now, how will you get a horizontal wire? Well, one way is to make such vertical wires and then break these wires and drop them on the substrate. That is how one can get horizontal wires. Okay. Now, for modeling purposes, what one does is one makes a simplified diagram where this is the wire and surrounding the wire, you have the metal. This is an example of a side bonded contact. And then this is used for analysis. Now let's look at end bonded contacts, right? So here is an example of an end bonded contact. These are because the contact is being made at the end of the wire. Similarly, the substrate is making an end bonded contact to the vertical wire. Now here is an example of a field effect transistor. Okay, how it is made, please look at it. So the wire is there, and you have top is an end bonded drain contact, bottom is a source contact, end bonded again. You can see how it is. Can anybody tell me what is this this blue region in between? This blue region? What do you think this is? Anyone? It doesn't matter if you make a mistake also. I just want
Is it insulation materials?
Yes, you are right. It is an insulating.
SiO2 layer, insulating layer.
Yeah. Why is it an insulating material?
Because of gate or source are not connected directly. Drain or source is not directly connected to gate.
Correct. So the drain and source should not get shorted. Now you see how the gate is. Gate is surrounding the wire. So here again you have an insulator. You can see this is also blue. This color also is blue. This is also blue. So similar material both. These are insulators. Okay. It is written here aluminum oxide gate dielectric. Okay. So this is an insulating aluminum oxide. On the top of that, there is this gate sitting. It can be made of metal. It could be polysilicon, whatever. Now, all these gates should be connected together. So that is what has been achieved using this flat part, which gets connected to all this. So that is how you get a gate contact. Now, the gate contact should not get shorted to the source contact. So in between, you are putting an insulating material. Okay. So this is how a field effect transistor is made. This is gallium nitride nanowire, but wire can be silicon and other materials also. Okay. Now, here is the modeled structure. I mean, for modeling, if you want to use, right? So we show a simplified diagram. This is the wire, and at the end, this is a metal piece. And please note, it is very important to note that this metal piece is extending beyond the wire. It is not restricted to the wire alone because it is a nano wire. This diameter is very, very small. So definitely this metal that you use to connect is going to be bigger than the wire. Okay, let's look at this was a schematic diagram, right? That is a difference. Whereas this is a real diagram, right? Real photograph of something. So let us look at a real photograph of a vertical nanowire FET. It is trying to implement this particular concept. You can see here, this is the wire. It is not straight, right? Because in practice, that is how it becomes. And then this is the gate coming from the two sides. Okay. And top, this is the source connection, and this is the drain, bottom. Using this kind of wires, this has been made. HILO, what does it stand for? Anybody can tell? What does HILO stand for? Anyone? Okay, I'm not getting a response. So high low. Okay, high low junction. You can have, so this is an example of a high low. What is the meaning of a high low junction? Anybody now that I have said what is HILO? High low. What is the meaning of a high low junction?
In terms of dielectrics.
No.
Okay.
It doesn't have to do with
Terms of
dielectric.
conduction, sir?
In terms of voltage, sir?
No, not even voltage.
Sir, in terms of inversion, on, off.
In terms of what?
Inversion, on, off, on, off.
No, that is also not correct. So high low refers to the doping levels on the two sides of the junction. So you can see here, one side of the junction doping level is high, other side is low. Okay, but both dopings are of the same polarity. This is very important. A high low junction is a junction between two regions which have the same polarity of doping, but one doping is higher than the other doping. Then it is called high low. What is a PN junction? One side doping is P type, other side doping is N type. What is a Schottky junction? One side is metal, other side is semiconductor, and the metal to semiconductor contact has a rectifying property. Then it is Schottky. What is an ohmic junction or ohmic contact? It is a metal to semiconductor contact, which is non-rectifying, which is like which follows Ohm's law, right? So these are the different nomenclatures we should be familiar with. PN junction, high-low junction, Schottky junction, ohmic junction, right? So you can replace junction by contact if you want. The word junction by contact. Okay. So I have told you that first we are going to talk about nanowires and different contacts, different types of contacts. So that is what we have seen: end bonded contact, side bonded contact, depending on the nature of bonding. High-low, Schottky, okay, PN contacts. These are also other types of contacts, right? Okay. Now, so PN, just now I mentioned to you PN. So this is an example of a PN junction. So part of this wire is P-type and remaining part is N-type. Then it is a PN. Here you have high-low, this part. So here is another device, this electromechanical switch made using nanowire. So this is the nanowire. Okay. So this is the top view and this is the cross section. If I take a cut line here, how it will look. This is how it looks like. When you apply voltage between these two, then the wire will bend, okay, because of electrostatic force of attraction, and then it will come and touch this contact. So that is why it's called an electromechanical switch. You can also make kind of transistor using this principle, where this gate is used to bend this wire and make a contact to the drain. So when you apply a voltage, a connection will be established by the wire between source and drain because of this bending. Okay, now let's talk about what are the characteristics that are observed. So one of the odd observation has been, I call it odd because it is unexpected. Orders of magnitude higher than intrinsic carrier concentration has been extracted from current voltage measurements of undoped nanowires grown on heavily doped substrates. So look at this kind of a arrangement where the wire is being characterized. This is wire. This wire, no doping was done during growth. The substrate was heavily doped. Okay. So in such a situation, actually, since doping in the wire is negligible, if you pass current through this wire and see the resistance and then have a model for that resistance and calculate back what is the doping, you should get very, very low doping, right? Unfortunately, what the observation shows is that the carrier concentration seems to be much higher than intrinsic carrier concentration. So how can you explain this? This is one of the observations. Another observation is even for nanowire with ohmic contacts, okay, the current voltage curve looks like this, which is not linear. So how do we say, what do you mean by nanowire with ohmic contacts? If consider a situation like this, if this region was not a wire, but instead a full bulk material, a bigger material, and the same metal was put, right, we would have got a linear current voltage curve. But moment you reduce the size of the semiconductor to a wire, shape of the curve has changed. Okay, so what is the explanation for this? We have to see what is the explanation. These are some of the observations. Let us look at another observation, anomalous observation. This is for the field effect transistor shown here. Now, how many of you know the operation of a field effect transistor? Please say yes in the chat. How many of you know the operation of the transistor? So please tell me how many yeses are coming.
We got 4S from
Sorry?
Vaslu, Chandrasekhar sir, and Shyam Pateti and Rajashekhar and Sandhya all sent yes only, sir.
Okay, let's pick one of them. Who you said Sandhya, is it?
Yes, sir.
Yeah, Sandhya, can you please turn on your video? Sandhya? Yes, are we getting the video on? No. So who else? And someone else who knows about field effect transistor and who has not interacted so far, please turn on your video. Anyone?
Professor Chandrasekhar sir, are you there?
He has actually interacted. Anybody else?
Yes, drain current in field effect transistor is a function of gate to source voltage as well as drain to source voltage.
Yeah. So in other words, the current between drain and source is controlled by the gate.
Yes. Just like a tap, water tap, there is a drain. So how we are controlling water through wheel?
Yeah.
So current is we are controlling by applying some voltage. That voltage creates a field. That's why it is called the field effect transistor.
Right. So current versus voltage. Okay.
Shockley given an equation.
Yes.
That is, drain current is a function of gate to source.
Yeah.
It is just like a parabola.
Right. Okay. Thank you. So now let's proceed further. You can see here, current voltage characteristics are shown here. When you increase the voltage, for some voltage, current is 0, but beyond some voltage, the current starts increasing. Okay. Now, the amount of current is a function of VDS also. So VGS is gate to source voltage. Look at the structure here. This is gate. This is source. And this is drain. So you're applying a voltage between gate and source. And you're also applying a voltage between drain and source. Okay. You're keeping the voltage across the drain and source constant. Let us say you are keeping it at minus 2.5 volts or minus 1.75 volts or minus 1 volt like that. So keep the drain to source voltage constant and vary the gate to source voltage. That is voltage between these two. Then you will sweep a curve. So those are the curves for different drain to source voltage. These are the different curves. Now, what is shown here is actually in this device, when current voltage curve was measured, you got these blue curves. Okay. But if artificially you remove this, instead of extending this source so much, you restrict it only to the wire. Don't extend the source. So LE stands for extension of the source. E stands for extension. L is length of the extension. Okay. So here length of the extension is 550 nanometers. That is because that is what it is in this diagram. Okay. Here it is shown as 100 nanometers. That is because in this photograph is not, the entire device is not shown, right? Now this is the measurement done on an actual device. So when the extension of the source on either side was 550 nanometers, you got these curves, blue. When that extension was reduced to zero, the curve changed, okay, to these red curves. Significant change one can see. Drain to gate, LDG, distance is 665 nanometers, drain to gate. So this is the drain and this is the gate. This distance is 665. Okay, so this gives you an idea of the size of. Now, here I would like to pause and just check whether people have a feel of, so 665 nanometers is 0.665 microns. Okay. Now, how much is a micron? Does anyone have a feel? How much is a micron? Can someone tell me? For example, if I ask you the size of your room, you will say it is maybe 4 meters by 6 meters or something like that, right? You use meters.
Hair, thickness of hair, sir.
Yeah, who is this person who responded?
Pratyusha, sir.
Sorry, Pratyusha. Yeah, well, can you please introduce yourself? What are you doing?
Sir, I'm actually faculty in EC department, sir.
Where?
In Hyderabad, sir, Telangana.
Yeah, which college?
TKR Engineering College.
Okay, okay, thank you. Correct. So you can use our hair as a measure. So you know how much is the diameter of the hair? How much is the diameter of the hair, Pratyusha?
Some few microns exactly, I don't know, sir.
Okay, so
I know the analogy.
Yeah, correct. So diameter of the hair is 25 microns, at least 25 microns. Now, if diameter of the hair is 25 microns, and we are talking about 0.66 microns, that is 0.7 microns. So you can say approximately 1 micron. That 1 micron is 25 times thinner than the hair. 20 times thinner than the hair. So you can see what is the size. These are really, really small sizes. These devices are called nanoscale devices, right? So you should have a feel of this size of this device. Okay. So here what it shows is, so these kind of devices, when they are of so small size, they become very sensitive to the dimensions of the contacts. That is what this shows. When you change the dimension of the contact, the current voltage curves seem to change a lot. Okay, so now far we have made some observations, right? We have seen the structure and then we have made some observations, measurements and so on. Now we want to explain, give a theory for all this. So we start with first, what is this surrounding or ambient field? Surrounding or ambient field. This particular field is explained using a parallel plate capacitor, which all of us are familiar with. So when you have a large capacitor, which means these two plates are large. Okay, what is shown here is cross section. So the top view of this will be some rectangular plate. Okay. The field between these two plates, when you apply a voltage, it will be vertical mostly, but at the edge, you will have what is called fringing field lines like this. The field will not end. It will not be restricted to within the plate area. Okay. Now, this field is called ambient or surrounding field. Why is it called surrounding? Because the capacitor is limited to this area. So anything beyond this is the surrounding of the capacitor. Since this field is coming in the surrounding portion, or is also called the ambient, we refer to this as ambient or surrounding field. Okay, now reduce the size of the capacitor. Suppose you reduce the plate size, make it small like this. You can see that the vertical lines, number of vertical lines has reduced, but the fringing lines have not changed. So most of the field now you can see is due to fringing or the surrounding field. So now that is the nature of the field in a nanoscale device. The surrounding field effect seems to dominate, whereas in a bulk device, surrounding field effects are not considered. That is why, in fact, how many of you have seen a field picture shown for a capacitor where fringing field is also shown? How many of you have seen such a picture? So I'm talking about there are two types of pictures which are there. One picture shows only these vertical lines and another picture which shows vertical as well as this fringing field. I am saying how many of you have seen a picture which shows the fringing field also? Anyone?
Yes, sir.
Yes. Is there anyone who says yes?
No, sir. Someone has said not seen. Dhanlakshmi Murubaka has sent yes, sir.
Yeah, Dhanalakshmi, can you please interact? Please turn on your video.
Yes, sir.
Yeah, Yeah, please introduce yourself.
So myself, Anlakshmi, I'm also working as an assistant professor in Visakhapatnam, sir, Vignan's group.
Okay. Yes. So
Sir,
where are you?
sir, as I was dealing some VLSI like integrated circuits subjects, sir. So there I have come across this about the fringing fields, sir, because of which there is some field effect in the actual working of the transistor in the IC technology. So there I have studied this fringing fields, which is occurring at the corners of the capacitors, capacitor effects.
Right. Good. So that is
Excuse me, sir.
Yeah.
It's a Dr. Rajshekhar in Vigyan Bharat Institute of Technology, Hyderabad, sir.
Right.
Actually, my base is electrical and electronics, TEEE. While discussing about electrical machines also, we are discussing about a fringing effect.
Correct.
Yeah. At the end corner of the coil side also, we are having that magnetic field.
Yes. So fringing field need not be electric, it can be magnetic also. Good.
Yeah, it's magnetic actually.
Yeah. Thank you. Here we are talking about electric field in this particular case. Right. Okay. So now let's understand. Now I try to explain using this how presence of this field can explain some of these observations, like this curves changing from blue to red, or why shape should be like this, or why you are getting a concentration of carriers in the wire to be much higher than intrinsic, even when you are not doping the wire. So these explain how can we explain these things. Now let us look at that using the surrounding field. Okay, consider a wire like this. Okay, imagine that you have connected a cell to pass a current. Now, what kind of field will you see? So one field you will see is the field along the wire like this. And the other field you will see is surrounding field. Again, you would not have seen a diagram showing the surrounding field for a wire. You would have seen in school days or anywhere else just field being shown as though field is only inside the wire. That is not correct. That is not an accurate picture. Then why is it that people don't show the surrounding field? Can someone tell me? I have explained, I have given the reason so far, but I want to check if people have understood. Why is it that in diagrams that you come across in books and elsewhere, we have not shown so far the diagrams which you have come across? This field, red.
Field effect due to this fringing fields are negligible in bulky components.
Yeah, very good. Who is it? Who is this?
Pratyusha, sir.
Pratyusha. Yes, you are right. So mostly the diagrams are showing bulk devices only, bulk structures, which are of big size. Okay, they're not talking about these small size things. These small size things have become important only in last 10 to 15 years, right? Before that, we didn't have these small sizes. Okay, so you are right. That is why this is not shown. Otherwise, it will be present, but it may not have much impact in bulk device. Okay, so now let us explain how. So here is a simulation result. Okay, how the field surrounds a wire. This is the wire. This diagram has been generated using a device simulator. Can anyone tell me names of some simulators which can be used to get this kind of field? Now somebody will have to mute. I think some.
Kindly mute yourself.
Voice coming. Madam, please mute.
Yeah. Yes.
COMSOL multi-physics software we can do.
Correct. So you can have, there are softwares like,
COMSOL.
physics software. What is this? Some other names I want to give: Silvaco, Synopsys. These are all device simulation softwares. You can use them to generate this kind of diagrams to see how the field will be surrounding the wire. Then can someone tell me what are these blue lines here? What are these blue lines? What are these blue lines?
So line in the material, sir. Phase line in the material.
These lines. These lines. Yeah. What are these?
Field lines inside the material, sir.
No. The field lines will have an arrow, right? These lines don't have an arrow, these blue lines.
Yeah.
So what are these blue lines? So these are equipotential lines, right? These are equipotential lines. That is, along this line, the potential is uniform, right? So length of the wire is 1.25 microns. The thickness is 30 nanometers. Doping is 3 into 10 power 16 per centimeter cube. There are about 30 dopant atoms in this wire, if you calculate. How do you calculate? I would like each of you to do a simple calculation, right? Because whatever activities I'm asking you to do will really help you to get a good feel of what is meaning of a nano-sized device. What are all the things happen in a nano-sized device, right? That is why I'm asking you to do these activities, asking questions and all. If I did not ask you questions and make you answer, then you will not carry away any feeling for what is a nano-sized device and what are the effects. And applied voltage is say 0.5 volts. Here, this voltage is 0.5 compared to this. Now, I would like you to do a calculation and tell me from this data here, how do you get this number? Anyone, please do calculation and tell me from this data, how you get this number. I mean, all of you, I want all of you to calculate, but then after you do a calculation, anyone can tell me how you are getting it.
Is there any particular formula applicable for nano devices especially?
No. In fact, whatever I'm asking you to do, doesn't require special knowledge. Okay. It only requires, so people should understand what is the meaning of doping, of course. If you don't know what is doping, then you cannot answer the question. But what does it doping means? There are impurity atoms. Doping is nothing but impurity atoms. This wire is made of silicon. In that you are putting impurity atoms. Let us say phosphorus or boron. And the concentration of those atoms is 3 in 10 power 16 per centimeter cube. Okay. So how do you get this number of dopant atoms from the length, thickness of the wire and the doping in the wire? Anybody can tell me.
Few responded in chat box. Doping means adding impurities.
Correct. That is correct. Now what I'm saying is, how do you get the number 30 in that wire?
Based on atomic distance and its size.
No, you tell me the formula which should be used to get the number 30. The parameters given are length. Let's suppose length is L, thickness of the wire, that is same as diameter. Suppose diameter is D, thickness is D. So length is L, thickness is D. Doping is N. Suppose you say doping is N. So in terms of L, D and N, how do you get the number 30? Somebody should tell.
Sir,
yes.
Just considering it as a PN junction diode, and PN junction diode width is equal to 1 by 2 epsilon 1 by ND, square root of 1 by ND.
No, what is this epsilon?
That is the constant, dielectric constant.
Correct. But why do you need dielectric constant here? I'm asking number of dopant atoms in the wire, right?
Okay.
How do you show that there will be 30 dopant atoms in this wire?
Sir, is it dopant line by the area covered by the material?
Sorry, can you please repeat?
Sir, Doping content divided by the area of the material, sir.
No, you can see, no, see, that is what. So length dimension is there, diameter dimension is there, doping is per centimeter cube, right? So your formula should be such that all the length dimensions should go away, because finally it is only a number without any dimension.
Is it volume, sir?
Correct. So you tell me, so what is your formula?
That's the doping level divided by the material value.
See, this doping is per centimeter cube. If you divide by centimeter cube, you will get per centimeter power 6. So it can't be doping by volume. What should it be? Can you please correct yourself?
Doping into volume.
Doping into volume, because doping is per unit volume.
Yes,
so,
sir.
Volume of the wire. What is the volume of the wire?
It's a thickness into length into that.
So
square material, sir?
See, wire, please tell me what is the shape of the wire, cross section of the wire, what are we assuming?
It's a circular, so it's a YML by R square H.
So tell me, what is the volume? Length is L, diameter is D. So what is the volume of the wire? So what is the volume of a cylinder of length L and diameter D?
Yes, sir.
This everybody, even a school child should be able to tell this, right?
Yeah.
Yeah, what is it? Yeah, what is it?
IR square L, sir.
Correct. So instead of R, here we are talking about thickness. That
thickness. Is. So it will be R 15 nanometer.
So pi, correct. So pi into 15
nanometer square into 1.68 micrometer.
Into length. Okay, you do that and then multiply that by this 3 × 10 power 16, you will get 30. Okay, so many dopant atoms are there in this. Now this is about 12:50. We started off around 11:45. Okay, 12:50. So 1 hour we have covered. Do you think we need a 5-minute break? I just want to know.
No, sir, please proceed.
Okay, we don't. So let me periodically, I have to get this response from the participants. If you don't want a break, please type in the chat. No. If you want a type yes in the chat. Let us see what is the response. Please tell.
No, sir, please continue.
Yeah. I just want some response from the participants. Let's see. Those who don't want break, please tell no in the chat. Tell me what are we getting?
We're asking you to continue.
Okay, good. Fine. Okay. So now let us look at the effect of the surrounding field. Now this is the surrounding field. So I have shown by simulation how that, this is the surrounding field. So now I will show how do you get the effect of this? Now, this is the effect. Potential versus distance is what is plotted by simulation. Potential versus distance. So in other words, distance starts from 0 to top. That means it is like this. I'm moving like this. So bottom potential is 0 and I'm moving like this. How the potential is going to vary without surrounding field. That is, if this field is neglected and you just like an ohmic, in other words, only this field, then you will get a straight line. Potential will vary linearly from bottom to top. But when you take this into account, the simulation shows that the potential varies like this, right? It is non-linear. This is the effect of the surrounding field, which is there because of the nanoscale. When you see the effect of that in current voltage characteristics, you get this red curve with the surrounding field. A slight non-linearity is introduced. Without the surrounding field, it is Ohm's law. Current versus voltage is linear. Okay. So this is how surrounding field can explain the non-linear shape. You can connect it to this, what I showed earlier. Okay, something like this. And now I'm coming here by simulation. This was measured data. This is measured data. From simulation, we are showing it is like this. Okay, it is not exactly what we have shown there, but somewhat like that. This is also S, right? Here also it is S, like this. Here also it is S. Okay, fine. Let's move on further. How do you simulate the effects and see? So the same thing, ambient field or surrounding field is shown here. You have field like this and the difference. So what is the difference between this and the previous thing? Previous case, we are considering only a wire. Here we are considering a junction. Is that clear? Please note the title. Here we are talking about junctions, whereas the previous case was simply a wire. I'll show you the previous again so that you can see the difference. This was the previous. This was a nanowire resistor. We are not considering junction here. Okay, we are considering this the wire. Whereas now we are moving to a junction because we understood a wire. We want to now go to a junction and understand this. So nanowires may be grown over substrates and contacted either individually using an STM tip or in parallel by a conducting overlayer. So these are the two cases that are shown. A single wire being contacted by a tip. On the other hand, you can have a large number of wires. All these are being contacted together by a polysilicon layer deposited, right? So you have a large number, all these vertical wires. These wires are there. And on the top of this, you put a layer of polysilicon. Of course, that layer will sit on what? So first you put a dielectric, like here, silicon dioxide is put. So you have the substrate, you put silicon dioxide everywhere. Then on the top of silicon dioxide, you put this conducting layer. That conducting layer will connect all the tips. This is another option. Okay. So both types of things are possible. Right. Now you do a simulation. So how do you do a simulation? Here is an example of a simulation setup. Then first you have to declare how the current is going to flow. So transport is by drift diffusion because the distance between contacts is large. Though it is in nanoscale, but still it is large to allow drift diffusion. Quantum effects are neglected since wire diameter is thick, more than 10 nanometers. Non-local tunneling through Schottky contact included. Okay, so here Schottky contact, tunneling current can also be there. Then mobility is going to vary. Okay, and interface charge is there, but we are neglecting it. And we assume that there is a rotational symmetry. That is why we are showing only one part, half, not showing the full. If you show the full, this will go like this. That wire will be here, substrate will be there here. Okay. In other words, full picture will look like this. Now what has been done, you have cut like this, just one half you are showing. Now classical equations of analysis, namely drift diffusion, transport, continuity and Poisson's equation are solved simultaneously using Centaurus. I would like to know how many of the audience here knows Poisson's equation. Please turn on your videos. How many of you know Poisson's equations? Turn on your videos.
Sir, Neeraj Gupta questioned that why we neglected quantum effects.
He's asking, is it?
Yes, sir.
Yeah. Anybody else can answer that question, please? Let me go back to that slide.
It's greater than 10 nanometer, no, sir.
What is greater than 10 nanometer?
Why? Because the distance between the contact is, as per that drift diffusion, it's greater than 500 nanometer.
See, that is correct. See, drift diffusion, we are this thing because it is greater than 500 nanometer.
Yes, sir.
But quantum mechanical because of this is because of this. This is 10 nanometer diameter. Sorry. Okay. So quantum effects will have to be included if the wire diameter is less than 10. Quantum effect don't have to do with between these 2 points because this distance is really very large. So that issue doesn't arise at all. But the diameter can be very, very small or it can be larger. So if the diameter is larger than 10 nanometers, you don't have to bother about confinement, quantum confinement inside the wire. Does that answer your question, Neeraj? Neeraj? Not getting a response.
Okay, sir. Yes, tell us.
Okay.
Okay, sir.
Right. Okay, Neeraj, what are you doing? You didn't introduce yourself.
Myself, Dr. Neeraj Gupta. Currently, I am working with MIT University, Haryana, and I have some interest in the device modeling.
Okay.
So that's why I am looking for new devices with new materials.
Okay. So
Especially the high electron mobility transistor.
okay. So where have you done your PhD?
I have done my PhD from MIT itself.
Which area?
Basically, it is in the device itself, device modeling.
Oh, which device did you model in during your PhD?
That is the cylindrical MOSFET.
Okay. Okay. Good. So now,
Thank you, sir.
Yeah, thank you. Now, can someone tell me what is the Poisson's equation? I'll give you a minute just to think about it and tell me what is the Poisson's equation. Because we are going more and more deeper into theory, so we should know these things.
It is a distribution of charge for the applied field. Theoretically.
No, what do we mean by distribution of charge? No, what does the equation tell? What does the, can you tell me the equation itself? So can you tell me the equation itself?
Sir, that is del dot E is equal to rho by epsilon naught.
Rho by epsilon, yes.
Yes.
Permittivity.
Yeah. Very good. Very
Charge
good.
density by permittivity. Yes.
Yeah. So del dot E is equal to rho by epsilon, where rho is the space charge, epsilon is the dielectric constant of the material in the space charge, and then E is the electric field. So divergence of electric field is rho by epsilon. You are right. But this form is not Poisson's equation. What is the name of this form of equation? There is another name. What is that name?
Maxwell's.
Sorry?
Maxwell's.
No.
Maxwell's equation.
No. No, it's not. That is not the name. Please try any other.
Laplace equation.
No, not Laplace equation.
Del square pi equals to rho by epsilon minus rho by epsilon.
So please repeat.
del square phi equal to minus rho by epsilon.
What is that equation? What is the name of this equation?
Poisson's equation.
Yes, you are right. So del square phi is equal to minus rho by epsilon is Poisson's equation, where phi is the, what is phi?
Potential.
Potential, correct. So now, yes, but in the other form that we just now talked about, divergence of E is rho by epsilon. What is the name of this form of equation? The name is Gauss's law.
Gauss's law in electric field.
Yeah, that is Gauss law. Okay.
And we replace E by minus delta V to make the Laplace equation.
Correct, correct. So no, to make it Poisson's equation, Now you tell me how Poisson's equation reduces to Laplace equation. Anybody tell me?
Equal to 0. We substitute that Poisson equation equal to 0.
So in other words, when the space charge is 0.
Yes.
Yes. Okay. Now, continuity equation. Now tell me, what is continuity equation? Anybody can tell me what is the, like you told, minus del square phi equal to rho by epsilon is Poisson's equation. Please tell me what is the continuity equation. Anyone? You can even look up, see, if you want to look up something because you have internet, you have all access. But I would like you to answer these questions, right? These are very important things.
So transport equation, sir?
No. I'm saying what is the continuity equation? Then you can tell what is the transport. Continuity equation, what is the formula?
So basically it is a charge density per unit time. D rho by dt.
Okay, and then what? Full equation you tell.
Sir, total positive charge is equal to total negative charge.
Who is the person who is telling this, please?
Sir, Praveena Rajput.
Praveena Rajput, good. Do you mind turning on your video? And what are you doing? Please introduce.
Sir, actually, I am working as an assistant professor in Guru Ghasidas Vishwavidyalaya, sir.
Acha, and what do you teach?
Yes, sir, I teach basic electronics, network theory. And presently, I'm doing, sir, my PhD. I'm making an organic thin film field effect transistor, sir. Top contact.
Okay, good. Thank you. Now, but then positive charge is equal to negative charge. That is not the statement of continuity equation. That is fine. So, I'm coming to know who are all my participants. That is really good.
Yes, sir. Yes.
Continuity equation. No, that is not.
Density is a function of time and length.
Sorry, please repeat.
Gives the relation between change in charge density as a function of both length and time.
No, but why didn't tell the equation itself? Like somebody told minus del square phi is equal to rho by epsilon is Poisson's equation. Like that continuity equation. Why can't?
Yes, sir. Del dot J equals to minus dou rho V by dou T.
Please. Is it Ravi speaking?
Yes, sir.
Ravi, please introduce yourself.
Yeah, my name is Ravi, sir, and I am doing PhD in NIT Warangal.
Okay, right. In which area?
Device modeling, sir.
Oh, good. Then you should be able to answer. Yes. So what did you say?
Del dot J equal to minus dou rho V by dou T.
Del dot. Del dot J, that is divergence of J is
yes, sir.
Now you are right. That is one of the one form of continuity equation. You are very much right. It comes as a part of Maxwell's equations, right?
Yes, sir.
Yeah. Okay. But here we are talking about a slightly different form of continuity equation. Okay, slightly different form of continuity. When I talk about the continuity equation here on this slide, it is not exactly that one. It is somewhat like that. You are right. But the equation that I'm talking about here. So you have to take into account also recombination and generation. this equation dou rho by dou t equal to divergence of J, that is called a displacement current equation, right?
Sir,
You have to take into account. Yes, somebody wanted to say something.
so dou n by dt is equal to the current density minus the recombination plus the generation.
No, you are almost correct. Please carefully check. Again, you tell the terms.
Dou n by dt is equal to 1 by q, the change in density with respect to the current density with respect to the distance,
Correct.
minus the recombination of electrons plus the generation.
Correct. So good. So it is, so you have two continuity equations, one for hole.
Holes and one for electrons.
Correct. So if you, for holes, if you want to tell what is the equation, it is dou p by dou t, where p is the whole concentration. Dou p by dou t is equal to minus 1 by divergence of Jp, that is current density due to holes, minus 1 by q, divergence of Jp, okay, plus generation rate minus the recombination. That is the continuity equation. Okay. Finally, drift diffusion equation. What is the drift diffusion equation? Anyone?
Current due to potential gradient and current due to concentration gradient.
Good, good. So please tell the equation. Who is the person speaking?
Chandrasekhar from
Chandrasekhar. I find only 4 or 5 people are responding, right? Like it happens in a class. So I think that 103 participants, but only, I think I would like others also to respond.
Jn due to electron.
Correct.
So drift is when there is
a E.
One by one. So one.
Mu n into E. Yes. Mu n
by,
or mu p
is the mobility of an electron or holes. N mu n.
So can you, all of you please please wait, let me. So I heard someone, Anita, were you speaking? Anita? Was Anita speaking sometime back?
Yes, sir. Yes, sir.
Yes, Anita, what is it?
Yes,
that
sir. So drift is when there is a field and there is a movement of electrons, we call it drift. And when there is a movement of electrons due to concentration gradient, we call it diffusion.
You are very correct. So what is the formula is what I am asking. Equation. So please tell, first of all, what is your, where are you teaching and what are you teaching?
Sir, I am Anita. I am working at as an assistant professor in the EEE department at Sri Venkateshwara College of Engineering, Chennai, sir. And I'm doing my PhD in the area of optoelectronics devices, fabrication of optoelectronic devices.
Okay.
I've not completed still, sir. I've just registered.
So what do you teach?
I teach electron devices and circuits, sir. I'm in the EEE department where I teach the semiconductor devices related subjects.
Right, right. So then you should be able to tell what is the equation for drift diffusion transport.
Yeah.
You can tell, what is it?
Just a minute, sir.
Sir, drift equation is J is equal to sigma E.
Drift equation is when I have.
Yeah, one by one. So Praveena, was it Praveena you spoke, right?
Yes, sir. Sir, drift is J equal to sigma E, where sigma is the conductivity.
Good.
And diffusion is dn by mu n is equal to dp by dx, which is due to the concentration gradient with respect to any distance x.
No. So what is the formula? Like J equal to sigma E is the current due to drift. J equal to what? J equal to what is diffusion?
Yes, sir.
Due to diffusion, what is the formula? J equal to?
J is sigma E.
by dx.
Yeah, one by one. See, Praveena, let Praveena tell. Let us see what she has.
Sir, J is the current density and sigma E is the applied electric field
No. Say 1 minute. See, Praveena, that is drift. I am asking for diffusion. What is the equation for diffusion?
Sir, dn by mu n is equal to dp by dx.
No.
No. That is
sorry.
dn into dou n by dx.
Dn into d.
Dou n
J
Q,
So
Q.
Jn,
You have to multiply charge.
correct. So Jn is equal to
dn into by d.
Q dn, dn by dx.
dn by dx.
dn is
Yes.
the diffusivity constant.
Yes.
Correct. Okay. So that is the drift diffusion. So these are the equations. So there will be two equations for transport,
Yes.
right? That is one for holes, another for electron.
Electrons.
Two continuity equations, one for holes, another for electron. And then there will be Poisson's equation, okay, or Gauss law. Okay, so these are solved simultaneously using Centaurus software. And that is how you are getting these kind of field pictures. Okay. And once again, the red lines here are field lines. And what are the blue lines? What are the blue lines?
Equipotential points.
Right, equipotential lines. Okay. So you want to understand operation of a device, you have to understand the operation in terms of these lines. Okay. Right. Now let us proceed further. Now, high-low junctions, let us consider them, n plus junctions with ohmic contacts. Okay. So here is the junction. These are the junctions, high-low. And there are contacts, ohmic. So where are the contacts? Wherever you are putting the metal, that is there, we are saying this is an ohmic contact. So you can also have Schottky contact, but here we are not considering Schottky contact. We are considering only ohmic contacts. So this red thing here and this red all over, these are all ohmic contacts. Okay. Similarly, for the substrate also at the bottom, you may have ohmic contacts. Okay. Now, same simulation has been done. And what we find is shown here. So when you simulate n on n plus like this, a wire whose radius is 15 nanometers, 30 nanometers, 100 nanometers, 500 nanometers. These are the variations which have been simulated. And what is shown here is the concentration of charge. Here, this concentration of charge, electron concentration versus distance. Okay, how it looks. So please note, what is the zero? The zero is this interface. This interface is zero. Okay, it is shown here clearly. You can see here 0. And as you move up, what is your distance? So the length of the wire is around 1 micron. Okay, you can see here. Go back. I'm sorry, it was in the previous slide. Okay. So not exactly, in fact, it is 1.25 micron. You can see here. This is 0 to 1 micron, and you have this extra. This is about 1, 2, 3, 4, 5, 1.2 microns actually. Length of the wire is 1.2. This is how the field is there. Now, where is the field starting from? It is starting from the n plus region here. And it is terminating on n. Can anybody tell me why there? Please see that no voltage has been applied here. No voltage is applied. Can you tell me what is the origin of this field? Why this field is there? Anyone?
Due to movement of intrinsic carriers in the
Pratyusha, yeah. What is that? Due to the
intrinsic carriers will be then say different diffusion.
So why should field is always from positive to negative. So you have to explain how positive charge is created, how negative charge is created.
Due to difference in the doping concentrations, there will be movement of charge carriers from one.
I know you are right. Can you please make it a little bit more clear? So which type of carrier will move and in which direction?
Here highly doped means electrons will be moving to load. Always charges move from high potential to high density to lower density. So from down to high, it will move towards upper. Electrons will be moving.
So from higher concentration to lower concentration. So electrons will move like this. And once electrons are moved, why field is created now? Can you tell?
Sir, the positive mobile ions which are left uncovered due to the doping.
Right, right. So once electrons move away from N plus, they leave behind positively charged dopant atoms, right? And they
Yes, sir.
give rise to positive charge. And here, it was neutral. This is gaining electrons from the N plus region. So it is becoming negative. That is why there is a field from positive to negative. Okay, so you can see now the electrons are coming into the wire from the substrate because of the process of diffusion. That is what is raising the concentration of electrons in the N-type region. Here it is given length of the wire is 1.25 micron and doping of the wire is 3 into 10 power 15. Okay, but what is the carrier concentration in the wire? If no carriers were coming from outside, carrier concentration would have been how much? If doping is 3 into 10 power 15, electron concentration also will be 3 into 10 power 15. It would have been the same. So you can see here, what is the picture? For 500 nanometer as radius, if this wire is very, very thick, okay, then your carrier concentration is flat as you go with the distance like this when you plot. So, and only when you approach zero, that is the substrate contact, the carrier concentration goes up. Okay. Otherwise, it remains equal to 3 in 10 power 15. But when you reduce the size of the wire, suppose you make it 15 nanometers instead of 500 nanometer. Now you can see how much is this concentration. Anybody should tell me, looking at this scale, how much is this concentration of electrons? From the scale, somebody should read and tell me.
Sir, 0.5.
So here you can see it is 0.3. Here it is 0.3 into 10 power 15.
Yes.
That is 3 into 10 power 15 actually.
Yes.
No, I'm sorry. This should be 10 power 16 and this is 0.3. It is written wrongly as 10 power 15. That is, no. I think it is correct. It is not, 1 minute. This is 0, 1. 10, yeah, yes. It should be 10 power 16 here actually. This is wrong. So 0.3 into 10 power 16 is 3 into 10 power 15. That is what is written. Yeah. So this is 3 into 10 power 15. So how much is this? How much is this? I have even placed the cursor there.
It's around
0.8.
8 into 10 to the power
8 into 10 power.
0.8.
Right. 8 in 10 power 15, which is 3 into 10 power 15 plus 5 into 10 power 15. So where are these carriers coming from? These extra electrons, where are they coming from? In this region, where are the extra electrons coming from? Huh?
N plus side.
I know, 3 plus 5. So where are they coming from, these extra electrons?
From N plus, sir?
Side.
Yes. So N plus, they got transferred from N plus here.
Yes, sir.
Okay, they got transferred. So this explains why your carrier concentration in the wire is different from the doping concentration once the wire diameter is progressively reduced. Okay, this is what I had said in the previous slide. Somehow the concentration of undoped wires also appears to be large. Okay, so this explains how it can be large. In other words, carriers are getting transferred into the wire from nearby heavily doped regions. Okay. Let me skip this analogy and all that. Now one can study. This is how you do research. One can study how this carrier concentration will change with various changes in the structure. So here examples are shown. So what are the changes in the structure? You change the length of the metal contact at the top. So this is here. It is the contact is restricted to the wire. Here it is extending beyond the wire. Here also it is limited to the wire. What is the difference between this and this? Somebody please tell me. What is the difference between this picture and this picture? Anyone?
That N plus is
on an N plus thin film, you have a N nanowire kind of structure.
Yeah. So here the N plus region is restricted to the wire.
Wire.
Whereas here it is extending.
Extended.
Okay. So we are trying to see the effect of extension of the contacts on the wire concentration in the wire. How these extensions have an effect. So this is what is shown here. You can see if both contacts are like that extended, then you get this carrier concentration versus distance curve. If bottom alone is extended, top is restricted, then you get this curve. If bottom is extended, top is extended little bit, not as much as bottom, then it will be in between. Like that. And how that is changing the carrier concentration. For example, if you have wire without a contact extensions, contacts are restricted to the wire diameter, then you have something like this with a flat portion. Okay. But moment you start extending the contact size, your carrier concentration is going on increasing. You can see that. Okay. So this can be advantageous or disadvantageous. Somewhere contacts are not required to be extended, but they get extended for some reason. That will affect the carrier concentration and hence the characteristics of the device. So now this is a crucial point. We had done this research. Other people were saying other reasons for getting the higher concentration in nanowire. So we have shown that actually in the nanowire higher concentration can come from nearby heavily doped regions itself. Okay, so I think with that I would like to, this other thing is complicated. Next thing, let us leave that. I think it is now 1:22. Maybe I will just stop here and take questions or anything like that. Questions, comments people may have.
Sir, very wonderful session, sir. We know deep knowledge about the basic physics about the devices. Thank you very much, sir.
Sir,
I would love some questions and see so many people didn't participate, right? Let me try, at least we should have some interaction and get to know our participants. So I see Pragyan Sahu. Pragyan Sahu. What happened suddenly, the screen?
Sir, excuse me, sir.
Yeah, 1 minute. The screen went off. I'm not able to see anybody.
Okay.
What happened? I don't know. What should I do? It says your screen sharing is paused. Okay, now I got back. No, I got back.
Oh, okay.
Sir, I have a question on my research. What I am doing, sir?
Right.
Sir, I am doing research on nanosheet FET, sir. So actually, I am just doing with nanowire and nanosheet and FinFET comparison, sir. I am getting better results with nanosheet compared to FinFET and nanowire, sir.
Okay.
So how can we can tell that which device is better for which technology when we go for sub 10 nanometer?
No, we have to tell. You should look at the specific situation and example, and then only you can tell. Right?
Okay, sir.
In general, you cannot say. But yeah, that is what. So evidently what will happen is in nano wire, confinement will be stronger than in a sheet.
Yes, width is less. That's why, no, sir.
So what happens is in a sheet, there is a confinement in a particular direction, but wire, entire surrounding, complete, it is, there is a difference between a sheet and a wire.
Okay, sir. Sir, but in nano wire, if it is cylindrical case, the width will be different from top to bottom vertically, no, sir.
No. So vertical part doesn't contribute to confinement. Vertical part doesn't contribute to confinement. If you want to, I think I understand your point. Let me see if I can draw a diagram and tell you. Just one sec. For that, I will have to again share. Just are you able to see my screen?
Yes, sir. Yes, sir.
Yeah, let me. So suppose you're talking about a sheet. Okay. I don't know why. Are you able to see my screen?
Yes, sir. Yes, sir.
Unfortunately, I am myself not able to. Just let me see one minute. Yeah. I want to draw something. So let me close things which will not help me. Yes, you're able to see this, right?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, now I will draw. So let us say if I'm drawing a sheet. Okay. Say this is a sheet. You're able to see this?
Yes, sir. Yes, sir.
Yeah. So, or let me make it a slightly different. Then it will be better. Let me make it like this. So this
Yes,
is
sir.
like a sheet. Now you can see. So here the confinement is like this in this direction and in this direction. Okay.
Okay, sir.
So confinement is like this. Now instead of that, now take a wire. So wire, what will happen is with same thickness, if you take a wire, let me see if I have a, yeah, here. This is a wire. Right, you can see it is the same thickness. But now for this, if you want to show the confinement, it will be like this as well as coming in that direction also, right? All surrounding.
Yes, sir.
The confinement will be from all sides, whereas here it is only one side. So that is why confinement in a wire is more than in a sheet. You have movement along this plane, isn't it? Movement in this direction is restricted, but movement in this direction is not restricted. Whereas in a wire, movement is restricted in this direction also and in the perpendicular direction also. That is, let me show that. So this direction also, its movement is like this. So it will be restricted like this. Okay, like this. That is the difference. Here it is only one direction restriction. Here it is from all directions. So confinements are stronger in a wire than in a sheet.
But on current will be less in nanowires compared to nanosheet, no, sir?
Yeah, because of confinement effects are stronger, things may be less in a wire. Yes. I mean, currents may be less.
Okay, sir.
Yes. Any other question? Any other question? Let's pick some people before we close. I see Ramesh Gurusamy. Ramesh Gurusamy.
Yes, sir.
Yeah, can you please introduce yourself? I will not ask any questions so that you don't feel uncomfortable. Just introduce yourself. What are you doing? That's all.
Sir, myself Ramesh. I am from Kalasalingam University.
Ah.
So I am basically doing with backend, sir. I am using this kind of transistor designing everything.
Okay. Okay. Thank you. What about Ashok Kumar? Ashok Kumar?
Yes, sir. Good afternoon.
Please tell us quickly what you are doing, and if you can turn on.
I'm a research scholar at Kalasalingam University, sir.
Can turn on your video.
Oh, 1 second, sir.
Yes.
Actually, it's very slow, sir. It's getting hanging.
Okay, fine. Thank you. That is fine. Okay. Okay. Anybody else? I see many other things. Shweta Chandar. Shweta Chandar? What are you doing and what are you teaching? Swapnil? Swapnil? Not getting any response. Anyone else? Rekha? First, am I audible to others?
Yes, sir, you are audible.
Okay. Prabhu Mani? Prabhu Mani. At least before leaving, let us interact a little bit. And then there is Syam Baddeti. What about Syam Baddeti? Rishabh Badjatia. Rishabh Badjatia. Yes, please tell us.
Hello.
Yeah, please tell us.
I'm working as
No, we are not audible. You are not audible at all.
I'm working as
Oh, sorry. Sorry. No, for some reason we are not audible. It's okay. Thank you. Thank you. Okay. Then Shabana Begum. What about Shabana Begum? Hello? Yeah. Okay. I think Charles or...
sir.
Yeah, maybe we will close the session.
Okay, sir. Thank you so much for your session, sir. It's really useful.
So shall I leave the meeting then? Thank you all.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.